A buck boost regulator provides an output voltage which may be less than or greater than the input voltage, hence the name buck boost. The output voltage polarity is opposite to that of the input voltage. This regulator is also known as an inverting regulator. This is the circuit diagram. The circuit operation can be divided into two modes. During the mode 1, the transistor Q1 is on and diode DM is reverse biased since the current flows in this direction. The input current which rises flows through the inductor L and the transistor Q1. In mode 2, the transistor Q is switched off and the current which was flowing through the inductor L would flow through inductor, capacitor, DM and the load. The energy stored in the inductor would be transferred to the load and the inductor current would fall until transistor Q1 is switched on again in the next cycle. These two are the equivalent circuits for mode 1 operation and mode 2 operation. Now, at VD, at this point, let us see how the voltage will be. During the turn on time, the voltage will be equal to Vs. During the turn off time, the voltage will be negative Vs. This is at VD. At I1, the current during turn on and during turn off. During turn on, the I1 is disconnected, which means the current will be 0. During turn off, the DM is connected and the current flows through the DM. That will be maximum to minimum. This is going to repeat during the turn on and turn off. Now, the output current IA will be continuous and constant. So, this will be a constant value. Now, the inductor current IL. During turn on, the IL is connected to Vs and is going to rise from its minimum value to the maximum value. The minimum value, let it be I1 and maximum value, let it be I2. And in mode 2, the inductor is going to discharge. So, current falls to minimum value. And this value between minimum and maximum is nothing but delta I, peak to peak current value. Now, the IC. During turn on, the IC value is going to depend upon the output value, that I0. So here, IC equals to minus I0, which equals to minus IA. So this is minus value during the turn on, minus IA. During the turn off of the transistor, now the IC is equals to IL minus I0, nothing but IA. And IL at KT will be max and reduces. And again, it will be negative. So this value is I2 minus IA. Now, the VC. During the turn on time, the VC fall from the maximum to minimum value. And during the turn off time, the VC is going to rise. And the difference between minimum and maximum value will be delta VC, which is peak to peak voltage value. And the average for this is VA. These are the current and voltage waveforms for turn on and turn off time. So the scale is KT during the turn on and full time T. Now if you want, you can draw all those separately. Now, assuming the current rises linearly from I1 to I2 during T1, that is turn on time of the transistor, then the voltage Vs equals to L, the current I2 minus I1 divided by the time T1. This is nothing but L delta I divided by T1 is our Vs. Let this be equation number 1. Now from which the T1 equals to L delta I divided by Vs. Let this be equation number 2. When the inductor current falls linearly from IT to I1 during T2, output voltage VA equals to the voltage across the capacitor minus L delta I by T2. Let this be equation number 3. Then T2 equals to minus L delta I by VA. This equation number 4. Now, the peak-to-peak ripple current of the inductor L from 1 and 3 delta I equals to Vs T1 divided by L, that equals to minus VA T2 by L. From this, VA equals to minus Vs T1 by T2. That is nothing but minus Vs T1 by T2. We can write T1 by capital T by 1 minus T1 by capital T. That is nothing but minus Vs of K divided by 1 minus K, which is VA. That is equation number 5. Assuming a lossless circuit, Vs Is equals to minus Va Ia, that equals to, substitute the value of Va from the equation number 5, then you will be getting Vs K by 1 minus K equals to Vs Is. This is multiplied by Ia. So Is equals to Ia K by 1 minus K. That is equation number 6. The switching period T equals to 1 by switching frequency F, that equals to T1 plus T2. Now substitute the value of T1, T2 from equation number 2 and 4, then delta I L by Vs minus delta I L by Va. Delta I L common, so Va minus Vs divided by Vs Va. Now let this be equation number 7. Delta I equals to time T by L Vs Va divided by Va minus Vs. Let this be equation number 8. Now this delta I, peak to peak ripple current in terms of switching frequency, Vs Va divided by Va minus Vs of L T is nothing but 1 by F. Equation number 9. Substitute the value of Va and simplify this, then you are going to get delta I equals to Vs K by Fl. This is equation number 10. Now, when transistor Q1 is on, the filter capacitor supplies the load current for T equals to T1. The average discharge current of the capacitor is IC equals to IA. And the peak to peak ripple voltage of the capacitor delta T C equals to 1 by C integral 0 to T1 IC dt. That equals to 1 by C 0 to T1 IA dt. Then delta Vc equals to 1 by C IA T1. And we know that the T1 equals to Va divided by Va minus Vs of F. When you substitute this in the above equation, then you are going to get delta Vc equals to Ia Va divided by Va minus Vs of Fc, or delta Vc equals to Ia K by Fc. A buck boost regulator provides output voltage polarities reversal without a transformer. It is having high efficiency. Now, under the fault condition of the transistor, the di by dt of the fault current is limited by the inductor L from this formula, and it will be Vs by L, as the peak to peak current is going to depend upon the inductor. The output short circuit protection will be easy to implement. However, the input current is discontinuous and a high peak current flows through the transistor Q1. This is regarding the buck boost regulator. You can call this as buck boost chopper, buck boost converter. If you find this video useful, please like, share, subscribe and comment.